Welcome back to another lecture on rings and ideals. In this lecture, we shall look at the Nilradical and the Jacobson radical of a ring A. Before going to the definition of Nilradical and Jacobson radical, we will prove this proposition which states that the set N of all nilpotent elements in a ring A forms an ideal of A. At this point, the learner could try to recall the definition of an ideal in a ring and also the definition of a nilpotent element in a ring. We will prove the result. Let N denote the set of all nilpotent elements in a ring A. We see that N is non-empty because the zero element of the ring belongs to N. Now we will try to verify the second condition in the definition of an ideal. So let us take an element A in A and X belonging to N. As X belongs to N, X power M is 0 for some natural number M. Now if we consider AX and raise it to the power M, we see that because of the commutative law in the ring A, we get AX raised to M is same as A power M into X power M, which is also equal to 0 since X power M is already 0. This says that AX belongs to N. Now we shall verify the first condition in the definition. Let us take two elements X, Y in N. Then by the definition of nilpotent element, we get X power M is 0 and Y power N is 0 for some M and N belonging to N, that is for any two natural numbers M and N. Now consider the binomial expansion of the term X plus Y to the power M plus N minus 1. Just see that M and N are both natural numbers, so that M plus N is greater than or equal to 2, and hence M plus N minus 1 is also a positive integer. Now if we use the binomial theorem here, because there is no problem in using binomial theorem as the ring is commutative ring, we see that every term in the binomial expansion will be a term of the form A into X power R into Y power S, where A is going to be some natural number and R and S are non-negative integers such that their sum is equal to the power M plus N minus 1. Now we claim that either R is greater than or equal to M, where R is the power of X in each of the term of the form A into X power R, Y power S, or S must be greater than or equal to N. What if the contrary, that is, if R is strictly less than M and also S is strictly less than N, or in other words, we get R is less than or equal to M minus 1 and S is less than or equal to N minus 1. This will imply R plus S is strictly less than M plus N minus 2, which is a contradiction because R plus S is equal to M plus N minus 1. Therefore, either R has to be greater than or equal to M or S has to be greater than or equal to N. One of these cases must occur. Now, if R is greater than or equal to M, we get X power R, which is written as X power R minus M plus M. We added and subtracted M here. And then we could write this power of X as X power R minus M into X power M. You see that both these powers are non-negative because of the fact R is greater than or equal to M. And since X power M is already 0, this product also becomes 0. That is, we get X power R is 0. Now, if S is greater than or equal to N, then we can write Y to the power S as Y to the power S minus N plus N, which could be written as Y power S minus N into Y power N, which is again 0 because Y power N is already 0. Thus, in any case, we see that either X to the power R is going to be equal to 0 or Y to the power S is equal to 0, so that each of the term of the form A into X power R into Y power S is 0. Therefore, we get X plus Y to the power M plus N minus 1. Because each of the term is 0, this power of X plus Y is also equal to 0, where M plus N minus 1 is a natural number. This says X plus Y is in the set of all nilpotent elements. Therefore, N is an ideal of A. The set of all nilpotent elements in a ring is always an ideal of A, and this special ideal is called as the nil radical of A. So the set N of all nilpotent elements in a ring A which forms an ideal of A, as we proved just now, is called as the nilradical of A. This is the definition of nilradical. Now we shall show that the quotient ring A by n has no nilpotent element other than 0, where n denotes the nilradical of A. Solution goes like this. As before, let n denote the set of all nilpotent elements in a ring A, and now consider the quotient ring A by n. Let us take an element x plus n to be a nilpotent element in A by n. Just remember that the elements in A by n are all cosets of the form x plus n, where x is in the ring A. So we have taken an element x plus n to be a nilpotent element in A by n. Then the definition of nilpotent element says that x plus n raised to some positive integer k must be equal to 0. Now using the definition of multiplication in the quotient ring, we get this as x power k plus n is equal to 0 plus n. Remember that the 0 in the quotient ring A by n is nothing but the coset 0 plus n. Now the equality of these two cosets implies x to the power k belongs to n, where again n is the nilradical of A, remember this. Now because x power k is in n, this implies x power k raised to some positive power m should be equal to 0. Sorry, this is not k, for some m belonging to n here. That is, x to the power k into m is 0, where k into m is also a natural number. This says that x belongs to n. That is, x is in the nilradical of A. But if x belongs to n, the coset represented by x, that is x plus n, must be same as 0 plus n. Thus, if we take x plus n to be a nilpotent element in A by n, this coset x plus n must be same as the 0 element in A by n. This says that the quotient ring A by n, where n is the nilradical, this quotient ring has no nilpotent elements other than the 0 element. That is, A by n has no non-zero nilpotent element. Now we shall prove a characterization of the nilradical of a ring. That is, we'll prove the theorem which states that the nilradical of a ring A is same as the intersection of all prime ideals of A. That is, n is equal to the intersection of P, where P varies over all the prime ideals of A. Nilradical, that is the set of all nilpotent elements in a ring A, is same as the intersection of all prime ideals in a ring A. We'll prove this theorem. First, we'll show that n is contained in intersection of all prime ideals of A. Let x belong to n. Then, as x is a nilpotent element, x power m is 0 for some natural number m. We know that every ideal in a ring always contains the 0 element, so as any prime ideal. So 0 belongs to P for every prime ideal P of A, and we see that 0 is also equal to x power m. So we get x power m belongs to P for every prime ideal P of A. Now a property of a prime ideal says that if x power m belongs to P, then x must be in P for every prime ideal P of A. This could be verified just using the definition of a prime ideal, because we know that a prime ideal is a proper ideal such that if x into y belongs to P, then one of the element has to be there in P. It can be extended by induction for any finite product of elements. Here we have x multiplied m times belongs to P. That implies x has to be in the prime ideal P, where P is any prime ideal of A. But if x belongs to every prime ideal of A, then x belongs to intersection of all prime ideals of A. Thus we have shown that n is contained in intersection of all prime ideals. Now we shall show that n contains the intersection of all prime ideals of A, that is the reverse inclusion. We will be proving this by assuming the contrary, that is, suppose x is not in n, then we will show that x cannot be in the intersection of all prime ideals. So suppose x is not in n, then x power k is not equal to 0 for any k belonging to n. x is not in the nil radical, so x to the power k is not equal to 0 for any natural number k. Now let us take S to be the collection of all ideals I of A such that x power k is not an I for any k in n. At this point, I would like to remind you all that the proof here for the reverse inclusion is using the same idea that we have used in proving the existence of a maximal ideal in a ring, where we construct a poset and then we try to prove that every chain in that poset has an upper bound in the poset, and then we apply the Zorn's lemma in order to construct the maximal ideal. So we will be using the same idea, but here the collection S that we are going to define is the collection of all ideals I of A such that x to the power k is not in I for any natural number k, where x is the same element which we are supposing that it is not in n. Then this S is non-empty because we can easily see that the zero ideal belongs to S, and I want the learner to verify this argument why zero ideal is in S. Once it is non-empty, we can partially order it with respect to set inclusion relation, that is S with respect to inclusion forms a partially ordered set. You can verify all the three conditions easily here, that is inclusion is reflexive, antisymmetric and transitive, so S is a poset now. And then consider any chain collection I alpha in S as we have done in that theorem which I mentioned. Then this chain, you can prove that it has an upper bound in S. Try to get an upper bound for this chain. Since the chain is arbitrary, this says that every chain in S has an upper bound in S. Therefore, by using Zorn's lemma, this poset S must have a maximal element. We'll call it as P. Now this maximal element P is in S, so that P must satisfy the definition of S. So as P belongs to S, x power k cannot belong to P for any k belonging to it. In particular, x itself is not in P. So we have found an element of the ring which is not in P. This says that P is not equal to A. So at this point we see that P is an ideal of A and P is not equal to A. Also, X is not an element of P. We will be proving now that this maximal element P is a prime ideal of A. The first condition is already there, that is P is a proper ideal of A. Now we'll try to verify the second condition in the definition of a prime ideal. That is, let us take two elements A, B in A such that A into B belongs to P. We have to prove that either A belongs to P or B belongs to P. So the claim here is either A belongs to P or B belongs to P. Again, assume the contrary. Suppose A is not in P and B is not in P. Then the ideal P will be properly contained in the sum of the two ideals, P plus ideal generated by A, and also P is properly contained in P plus ideal generated by B. Remember, P plus ideal generated by A and P plus ideal generated by B are sum of two ideals, so both of these are ideals. We have found two ideals now which contain P as a proper subset. So by the maximality of the ideal P in S, these two ideals which we got just now, that is P plus ideal generated by A and P plus ideal generated by B, cannot belong to S. And because they are not in S, there must exist positive integers m and n such that x to the power m must belong to P plus ideal generated by A and x power n must belong to P plus ideal generated by B. Recall that S is the collection of those ideals which do not contain any power of x, and because these two ideals, P plus ideal generated by A and P plus ideal generated by B, are not in S, they must contain some powers of S, x. This will imply that x to the power m plus n, remember x power m plus n is nothing but x power m into x power n, this power will belong to P. This is an easy observation. What you could do is, because x power m belongs to P plus ideal generated by A, you can write it as a sum of elements, one taken from each of the ideal. Similarly, write x power n as a sum of two elements, one taken from each of the ideals P and ideal generated by B. Then multiply them, and then you can easily observe that x to the power m plus n belongs to P, because A into B, somewhere you get the term which contains A into B, and A into B is already there in P, and P is an ideal of A. Thus, we have found a power of x which belongs to P. This is a contradiction because P is in S. S contains only those ideals which do not contain any power of x, whereas we found a power of x which belongs to P. Therefore, this is a contradiction. So, our claim holds, that is, either A must be in P or B must be in P. Thus, we have shown that P is an ideal which is not equal to A, and also if product AB belongs to P, then either A belongs to P or B belongs to P. This says that P is a prime ideal of A. Also, it does not contain X. It does not contain X implies that X does not belong to the intersection of all prime ideals of A. That is, if there is a prime ideal which does not contain x, then x cannot belong to the intersection of all the prime ideals. Thus, we have proved that if x is not an n, that is the Nilradical of A, then x does not belong to the intersection of all prime ideals of A. Or in other words, we have proved that n must contain all the elements of the intersection of all prime ideals of A. That is, n contains intersection of all prime ideals of A. Now, combining both the inclusions, because earlier we have proved that n is contained in intersection of all the prime ideals, we get the equality that n is equal to the intersection of all prime ideals of A. This proves the theorem. Now let us define what is the Jacobson radical of a ring A. Script J is the notation we are using here. The Jacobson radical J of a ring A is defined as the intersection of all maximal ideals of A. At this point, you could try to find the Jacobson radical of some familiar ring whose maximal ideals are known to you. Now let us give a characterization of Jacobson radical. It can be characterized as follows. So the next result gives a characterization. This theorem states that if A is a ring with the Jacobson radical J, then X belongs to the Jacobson radical if and only if 1 minus xy is a unit in A for all y belonging to A. So for an element x to be in the Jacobson radical, the if and only if condition is that 1 minus xy must be a unit for every y belonging to the ring A. We'll prove the direct implication first. Let x belong to J. J is the intersection of all maximal ideals. So we get x belongs to every maximal ideal of A. Now let us take an element y in A. Consider y belonging to A. Remember, we have to prove here 1 minus xy is a unit. Suppose the contrary. Say suppose 1 minus xy is not a unit in A. 1 minus xy is not a unit in A. We have already proved a result as a corollary of one of the theorems that a non-unit in a ring is always contained in a maximal ideal. There should exist a maximal ideal which contains a given non-unit element. Now we are supposing 1 minus xy is a non-unit in A, so there should exist a maximal ideal, say M, such that 1 minus xy belongs to M. So we get 1 minus xy belongs to M for some maximal ideal M of A. We also see that because x belongs to every maximal ideal, it is also present in this maximal ideal M, and an ideal is always closed under multiplication by ring elements, so that xy is an element in M. So we note that xy belongs to M since x belongs to M. And we also know that an ideal is closed under addition, so we get 1 minus xy, which is already in M, plus xy is also in M. But 1 minus xy plus xy gives us the identity element, that is 1 in the ring A. We get 1 belongs to M. This is a contradiction because Once the identity element belongs to an ideal, then it immediately implies that the ideal must be equal to the whole ring. So then we would get M is equal to A, but M cannot be equal to A because a maximal ideal is always a proper ideal. So 1 belonging to M gives us a contradiction. This says that 1 minus xy must be a unit in A. Thus we have proved the direct implication. Now let us go to the converse. So we shall take x in the ring A such that 1 minus xy is a unit in A for all y belonging to A. Remember, our aim is to prove that x belongs to J, the Jacobson radical of A. Again, suppose the contrary. Suppose x is not in J. Remember, J is the intersection of all maximal ideals. So if x is not in the intersection of all maximal ideals, there should exist a maximal ideal, say M naught of A, such that x does not belong to. So because x is not in J, then we get x does not belong to M naught for some maximal ideal M naught of A. Because x is not in M naught, if we consider the ideal M naught plus ideal generated by x, this ideal will properly contain M naught as a subset. That is, M naught is properly contained in M naught plus ideal generated by x because x is not in M naught. But then we would get M naught plus ideal generated by x is equal to A, since M naught is a maximal ideal of A. Because our ring A contains the identity element, now we could represent 1 as sum of two elements, one taken from M naught and one taken from the ideal generated by x. So we are able to express 1 as z plus ax, where z belongs to M naught and A is any ring element. Now rearranging the terms, we would get z is equal to 1 minus ax, and our hypothesis in the converse says that any element of the form 1 minus xy, where y can be any ring element, is always a unit. Now 1 minus ax, or we could also write it as 1 minus xa, because the ring A is a commutative ring. This element must be a unit in A by our hypothesis. That is, we get z is a unit in A. We see that z is an element in M naught, which is a unit now, but if a unit element belongs to an ideal, that ideal must be equal to the whole ring, which is again a contradiction because a maximal ideal M naught is a proper ideal of A. Therefore, our supposition fails here, that is, x must belong to J. Thus, we have proved that an element x belongs to the Jacobson radical of a ring A if and only if 1 minus xy is a unit in A for all y belonging to